students, welcome to my channel iSmile Academy. I am Professor Ismail Papadia. Here we will discuss some problems based on semiconductor. So starting with part 1, the first question is, if the energy band gap of carbon, germanium and silicon are compared, so what do we get? So here we see the values of energy band gap of carbon, silicon, germanium. Carbon is around 5.5 electron volt, silicon is 1.1 electron volt, germanium is 0.7 electron volt. So if we compare it, so carbon is having the largest energy band gap, silicon lesser than that, and germanium is lesser than that. So if we compare it, carbon is having the largest energy band gap, and germanium is the least one in the given problem. So here the answer is the first one, EC is greater than ES, which is greater than EG. Next, if the energy of photon of sodium light lambda 589 nanometers equals the band gap of semiconductor, the minimum energy required to create electron hole pairs or hole electron pairs is. So how to solve this? So here what we are given is the wavelength. Wavelength is 589 nanometer. We convert this into meters, 589 into 10 raised to minus 9 meters. Okay. Then what we know, how do we write the energy equation? Energy is equal to H into F, where H is Planck's constant, F is the frequency, but in our case we are given wavelength. So we convert this frequency to wavelength. We know frequency is c upon lambda, where c is the velocity of light and lambda is the wavelength. So we convert this. Then H, we substitute the values H, C. H is a constant 6.6 10 raised to minus 34. C is again a constant 3 into 10 raised to 8 meter per second, and lambda is we know, and we substitute these values, and when we calculate we get 3.3 into 10 raised to minus 19 joules. Now remember here in this case the answer which is given in the options is in terms of electron volts. So when we want to convert joules to electron volts, we divide it by E, that is 1.6 into 10 raised to minus 19. So we convert this joules to electron volt by dividing this value by 1.6 into 10 raised to minus 19, which is the answer is 2.1 electron volt. Okay. So here we have the answer is 2.1 electron volt. Next, the maximum wavelength of electromagnetic radiation which can create a hole electron pair in germanium, Eg is given 1.72 electron volt is. Okay. So here in the previous problem we need to calculate we had to calculate the energy. In this case we need to calculate the wavelength. So it is almost similar to previous one, only some conversions like Eg is given to us. Eg, energy band gap of germanium, is 1.72 electron volt. Now we convert this into joules. Okay, so here when we want to convert from electron volt to joules, we multiply by 1.6 10 raised to minus 19. Okay, so we keep this value as it is. Now again E equal to HF, but in our case we are interested in calculating the wavelength, so we convert this frequency to wavelength by C upon lambda, F equal to C upon lambda, then we calculate lambda. So this is what the substitutions are as in the previous case. Okay, now after doing the calculation, okay, I suggest in all my videos for the students, just don't watch the videos, but apart from watching the videos you must solve this problem by yourself also. So what we get, lambda is 7.07 10 raised to minus 7 meters. Okay, so this is the answer. Okay, so this is this answer is actually matching with this one, 7.1 10. So this is one is closer, so this is the answer. Next, the probability of electrons to be found in conduction band of an intrinsic semiconductor at finite temperature, it increases exponentially with increasing band gap, or decreases exponentially with the increasing band gap, or decreases with increasing temperature, or is independent of the temperature and band gap. So here what the probability of finding the electron in the conduction band of an intrinsic semiconductor. So what is the probability of finding electron in the conduction band of intrinsic semiconductor? What is the meaning of intrinsic? Intrinsic semiconductor is a pure semiconductor. Okay, so here see what we see here in this case. This is the energy band diagram. the blue part is the conduction band and the red is the valence band, and there is a gap between the conduction band and the valence band. So at room temperature, okay, what we observe is valence band is full of electron, but there are very few electrons in the conduction band. Okay, so probability of finding the electron decreases exponentially with the as the band gap increases, because more energy is required to overcome the band gap. So we need to supply some energy to push these electrons from valence band to conduction band, and it increase. Okay, so because we need to put large amount of energy, okay, so the probability of finding the electron decreases exponentially with the band gap. Okay, so this is the answer here. Okay, so it increases exponentially with increasing the band gap. Now here you can also compare other answers which are of course absurd in this case. They are never true. So decreases how it can decrease? Okay, it will always increase. It decreases with increasing temperature. Okay, but in this case, if we increase the temperature, more electrons are excited. Okay, so this is also not true. And the last one is independent of the temperature, which is false, because it depends also on temperature. Okay. Next, an intrinsic semiconductor has resistivity of 0.50 ohms. Find the carrier concentration if the mobility of electrons and holes are 0.39 meter square volt inverse second inverse, okay, and 0.11 meter square volt inverse and second inverse respectively. Okay, so we need to find the carrier concentration. Okay, so some things are given. In this case we are given some parameters. Okay, so first of all, let us see what is the meaning of resistivity. Okay, so resistivity, actually we will learn some terms. We are not only doing problems, but we must also learn some theory part. Okay, so it is the physical property of a particular element having particular dimensions. The unit of resistivity is ohm meter. Okay, so if you compare with resistance, it is ohms, but resistivity is ohm meter, and resistivity is only proportional to the nature and temperature of the particular material. Then comes mobility. Mobility is a measure of how quickly an electron can move through a metal or semiconductor in presence of electric field. Okay, how it can move in the presence of an electric field. Then semiconductor mobility depends on impurity concentrations, defect concentrations, temperatures, and electron hole concentrations. Please remember these things, because it might happen that questions may be asked on base of these definitions as well as the factors which are affecting the mobility. Okay, now we come to the problem. So we are given the resistivity. Okay, we define it by rho. Then mobility of electron and hole are given. Okay, so this is the formula, okay, for finding the resistivity. 1 upon rho is equal to E. Okay, E is the charge, Ni mu E plus Ni mu H. Mu is the mobility of electron, mu H is mobility of holes. Okay, so only one thing is not given, Ni is not given, so we need to find Ni. Okay, so Ni is the carrier concentration. Okay, so Ni is equal to, we just cross multiply, rho is given, E is again 1.6 10 to minus 19. Okay, and this we substitute the values of mu and mu H which are given. So finally we get it is 2.5 into 10 to 19 per meter cube. Okay, or meter m raised to minus 3. Okay, or per meter cube. So in this case, okay, we get the answer. Okay, now this is 2.5, and here of course this second B is the answer. Next, the mobility of electrons and holes in a sample of intrinsic semiconductors at room temperature are 0.54 meter square volt inverse, second inverse, and 0.18 respectively. If electron and hole densities are equal to 1.5 10 to 19 per meter cube, the conductivity of the semiconductor. So in this case we are given the mobilities of electrons and holes, and that electron hole densities are given. We need to find the conductivity. Okay, so how to find the conductivity in this case? See, conductivity is reciprocal of resistivity. Okay, so 1 upon rho is equal, as we have seen in the previous case, we need to remember this formula. So here we get it straightforward. Okay, E Ni mu E plus Ni mu H, we just substitute the values, okay, the given values we substitute and we can find it easily. Okay, so it is around 1.7 Siemens per meter. Okay, so to see the units of conductivity, Siemens per meter or Siemens meter inverse. Okay, so this is how we get it. Next, in an n-type semiconductor, which of the following statements are true? Okay, so here electrons are majority carriers and trivalent atoms are dopants. Electrons are minority carriers and pentavalent atoms are dopants. Holes are majority carriers and trivalent atoms are dopants, and holes are minority carriers and pentavalent atoms are dopants. Okay, so here let us see the theory part first. So here you can see this is a pentavalent or we can say n-type semiconductor. So here this is silicon. Here at this point, this one is a antimony. Okay, and we are when we add antimony to any pure semiconductor, we get n-type semiconductor. So every silicon atom, it has 4 electrons in the outermost shell, but antimony has 5 electrons in the outermost shell. So every antimony which is surrounded by silicon, it shares its 4 electrons with the silicon and 1 electron is left free. Okay, so here what we get is in this case, so here in this case holes are minority carriers and pentavalent atoms are dopants. Okay, so whenever we add pentavalent atoms, the resulting semiconductor becomes n-type semiconductor. Okay. Next, if a small amount of antimony, of antimony is added to germanium crystal, its resistance increases, it becomes a p-type semiconductor. There will be more free electrons than holes in the semiconductor, or none of these. So here let us see what are the types of impurities we are given. See, doping elements. Doping means the impurities which we are adding to a pure semiconductor. So here 2 columns are given, p-type and n-type. So if this boron, these elements, the boron, gallium, indium and aluminum, whenever they are added to a pure semiconductor, we get p-type semiconductor. On the right side we have phosphorus, arsenic, antimony and bismuth. When these impurities are added, we get n-type semiconductor. So here in our case what we are given is when we add antimony is a semiconductor. So when we add antimony, there will be more free electrons than holes. Okay, so if we would have added any p-type semiconductor, then we would have more holes. Okay, but here in this case we have more free electrons. Next, when a donor impurity is added to a pure semiconductor, then the donor level lies close to the Fermi level, below Fermi level, below and close to conduction energy level, or above and close to valence energy level. So here, see in this case, you can see this diagram. Okay, so a donor level means what? We are adding a pentavalent impurity. So donor level, it lies close to the conduction band, but it is below the conduction band. And acceptor level, when we are adding any p types, when we are adding any trivalent impurity, then we are adding more holes. So in that case, the acceptor levels, they are closer to valence band and above the valence band. Okay, so in this case what the answer is, it is below and close to conduction level. Okay, so donor means one which is donating electrons. Okay, suppose if we had here acceptor levels impurity, then it would be above and close to valence shell, but in this case below and close to conduction level and energy level. The last one for today, a semiconductor has equal number of electrons and hole, concentration of 6 into 10⁸ per meter cube. On doping with certain impurity, electron concentration increases to 9 into 10⁻12 per meter cube. The new hole concentration is, so we are given electron hole concentration and we are adding some electron, okay, whose concentration is because of doping, the electron concentration increases by this amount. So what is the hole concentration in this? Okay, so here we'll see the formula. Here in the solution we have this, Ni is given, Ni is same for both. We are adding electron impurity, that is we are adding impurity, so electron concentration becomes 9 into 10⁻12. This is the formula, Ni square equal to Ne and Nh. Ne is the electron concentration NH is the whole concentration. So Ni is given, Ne is given, we want to find NH. So this is how we find it. Okay, we substitute the values and finally we get 4 into 10⁴ per meter cube. That's all for today, students. Okay, please revise, okay, and go through the problems and solve the problems yourself. Okay, all the best.